Going to talk about analyzing calculus functions using both the function itself, as in this problem, as well as the graph of the first derivative. And for each of these functions, we're going to find the critical values where f is increasing, decreasing, its relative, or otherwise known as its local extrema, its concavity, and its points of inflection. So first, when you talk about the critical values, the plan is to take f prime of x, set it equal to 0, and also where f prime is undefined. And then solve for x, and those will be your critical values. So when we take this derivative, we're going to use the power rule. So f prime is going to be 3x squared plus 4x minus 15. And when you factor this expression, you're going to get 3x minus 5 and x plus 3 equal to f prime. Now, there's no place where f prime will be undefined, so the only critical values we're going to be dealing with are those that you get when you set f prime equal to 0. So we're going to use the product rule, zero product rule, and we're going to set 3x minus 5 equal to 0 and x plus 3 equal to 0. And when we do that, we're going to get the critical values of x equal to 5 over 3 and x equals negative 3. Okay, the next part of this is to do a sign analysis. So right now we're working to find out where f is increasing or decreasing. And to do that, we're going to do a sign analysis of the first derivative. So I like to label it, and I like to put the two factors down here and set up 3 zones like so, and then pick a value in each zone that will make my math easy. Okay, so in zone 1, I'm going to use negative 10. For zone 2, I'm going to use 0. And zone 3, I'm going to use positive 10. Folks, one thing I want to point out, if you ever have factors here with the first derivative that are to the second power, those are always going to be positive. You do not even need to include them in the sign analysis. It means nothing to add a positive sign when you're doing a sign analysis. It doesn't change things. So look for situations where you can take advantage of that and make your math a little bit easier. Okay, so in zone 1, if we plug in negative 10 here, that's going to be negative, negative, positive here in zone 1. If we plug in 0, whenever you plug in 0 to a function, put your thumb, or in this case your mouse, over any term or any expression that has an x in it and just ignore it. So that's going to be negative 5 times positive 3. That's going to be negative. And here, this is going to be positive and positive. So that is the sign analysis of the first derivative. Now, why is that helpful? Well, if your first derivative is positive, that means your f function has to be increasing in that interval. Why is that true? Let's say this is a function f. All right. In this interval, it's clearly increasing. As you move left to right, it is increasing, meaning its y values are going up. Any graph that's increasing, again, this is f, the parent graph. Any graph that is increasing, by definition, has a positive slope. Folks, the slope on the parent graph, on the f graph, the slope on the f graph is synonymous with the y value on the f prime graph. So if we have on the f prime graph a positive y value here, we know that that corresponds to a positive slope on the f graph. They are going to be the same. So we know that our f is going to be increasing here, decreasing here, and increasing there. That makes x equals negative 3 a local maximum, and x equals 5 over 3 a local minimum. Finishing up here, we found that we have a local maximum at x equals -3. In order to find the y value, you need to do f of -3. You plug the -3 back into the original function, not the derivative. And if you plug in 5/3 into the original function, you get this fraction shown here. Now, folks, suppose your teacher, for whatever reason, asks you to find the relative extrema using the second derivative test. So in the second derivative test, everything stays the same up until this point, meaning you still have to take the first derivative. You still have to get the critical values. And now what you do is you take the second derivative. So here the second derivative would equal 6x plus 4. And if we factor out a 2, we would have 3x plus 2. Now, to do the second derivative test for local extrema, you do f double prime, of each of the critical value points. And when you do this, you're only looking for the sign. You don't need the actual value. So you could see, if you plug in f double prime of 5/3, and you plug in 5/3 here, that's going to get you a positive. If the second derivative is positive, it means f itself is concave up. So that value right here has to be a local minimum. When you plug in -3 and you do f double prime of -3, you get a negative value. That corresponds to a concave down portion on f. Okay, this is f. And that means that x equals -3 is a local maximum. The second derivative test eliminates the need to do a sign analysis of f prime. But you still have to set f prime equal to 0 or where it's undefined. You still have to get its critical values, but you do not have to do a sign analysis of each interval unless they're asking you where the function is increasing and decreasing. If they just want the relative extrema, the local extrema, you can try the second derivative test and see if this works out. Now, of note, if you take the second derivative of a critical value and you get 0, or if you get undefined, that means the second derivative, which really can be thought of as a shortcut, has failed. So now you have to go back to the gold standard of f prime, and you have to go ahead and do a sign analysis, see where f is increasing and decreasing, and then determine what's a local minimum and local maximum by analyzing what's happening with these arrows. So in this case, if you do f prime at a critical value, and in this interval it's increasing and decreasing, then you know that is a local maximum. Now that we have found the function's critical values, where it's increasing and decreasing, and the local extrema, now let's move to concavity. If we had had a graph of the first derivative, like you're going to see later in the video, we don't need to take the second derivative. We can gather the information from the graph itself of the first derivative. But here we're only dealing with the function. And if you only have the function and you want concavity and points of inflection, you have to then evaluate the second derivative. Now, we already did that during our discussion of the second derivative test. When you take the second derivative, you have to set that to 0, and you have to set the second derivative to undefined and solve for x to get its critical values. You no longer use these from the first derivative. So when we do that, recall we factored out a 2, and we ended up with 3x plus 2 is our second derivative. This function is going to be defined for all real numbers, so we're not going to have any critical values from there. But when we set that equal to 0, we're going to get x equals -2/3. Now we're going to go ahead and test the do a sign test of the second derivative. So the second derivative is listed here. Folks, because that 2 is positive, we could leave it out of the discussion. That positive is not going to change anything here. So we're just going to look at 3x plus 2. So if we have negative 2/3 here, in this first interval, let's use negative 10. If we plug in negative 10 here, we're going to get a negative value. And for this interval, let's use positive 10, and we're going to get a positive value here. Folks, that means that this portion of f, because the second derivative is negative, is going to be concave down, looking like so. And this part of the function itself, the original function, because the second derivative is positive, is going to be concave up, like so. Now, because there's a change in concavity, specifically f is moving or changing from concave down to concave up, this becomes a point of inflection. So a point of inflection is the last on our list, on our to-do list. X equals 2/3 is indeed a point of inflection. If we had no change in concavity, we could still discuss the concavity of f, but let's say for argument's sake we had this show up on a different function. We could say that this portion of the graph is concave down, but this is no longer a point of inflection. A point of inflection means the concavity has to change as you move through the critical value. Folks, I want to point out something to be cognizant of. If you're given a function, this is 1 over x plus 4 squared, and we're asked to find where it's increasing, decreasing, and the relative extrema. We're going to go ahead and get the critical values. We're going to take the first derivative, which is shown here. We're going to set it equal to 0, which doesn't exist. There are no values of x to make that 0 because we have a constant in the numerator. But if we're asked to find where f prime is undefined, we would say that it is undefined at x equals -4. Then we would dutifully perform our sign analysis on the first derivative. So here's our first derivative, -2 over x plus 4 cubed. Unfortunately, we can't eliminate anything here because these can be negative. So we're going to go ahead and put our critical value of x equals -4 here. We're going to evaluate -10 here and +10 here. If we have -10 here, we're going to have a negative over a negative, and that's going to result in a positive function. And if we put a positive in here, the denominator is going to become positive, and the whole function is going to become negative. Therefore, we might be tempted to say, well, our function is increasing from -infinity to -4 and decreasing from -4 to +infinity, and we'd be correct in that case. But when we talk about local minimum or maximum, look at this. If this is increasing and that's decreasing, we'd be tempted to call that a local extrema. We'd be tempted to call that a local maximum. But folks, look, -4 does not exist in the original function. So it cannot be a relative or a local minimum or maximum. Here's the graph of this function. Let me go ahead and erase this to make it more clear. And you could see this is the graph of 1 over x plus 4 squared. This is -4. Folks, this is not a relative extrema. We do see the graph increasing from -infinity to -4 and decreasing from -4 to infinity, but there is no local extrema here. So whenever you think you have a local extrema, you have to go back and check the original function and make sure that that point exists on the original function. In our next example, we are given this function, f equals x to the fourth, and we are asked to find the points of inflection. Because we do not have the graph of the first derivative, like we will later in the video, it means whenever you see the words inflection or concavity, we have to go right to the second derivative and do a sign analysis of its critical points. And when I say its critical points, I mean those of the second derivative. So we will take f prime, but that is just a means to get to the second derivative. Meaning, when we're looking at points of inflection and concavity, we do not need the critical values of the first derivative. We only need the critical values of the first derivative for the second derivative test. But here, we're going to take the second derivative and do a sign analysis. So here we go. We're going to set f double prime equal to 0 and f double prime equal to undefined. The latter doesn't exist, but f double prime does equal 0 at x equals 0. Excuse me. We're going to go ahead and do a sign analysis at x equals 0. We're going to have two zones. Folks, look at this. That positive 12 is always a positive. That x squared is always a positive, meaning there's no x that you can put into the second derivative and get a negative value. That means this function is concave up to the left of 0, and it is also concave up to the right of 0, meaning this is not an inflection point. If the question asks to discuss concavity, we could say it's concave up everywhere. Well, concave up from negative infinity to 0 and from 0 to positive infinity, but in terms of points of inflection, none exist. Folks, this is what this graph looks like. It's very similar to the famous graph f of x equals x squared. The only thing is, when it hits the origin, there's a little bit of a hug here, and then it goes back up. So that's what I mean when I split the concavity, meaning it's concave up from negative infinity to 0, and then it's concave up from negative infinity to 0, and from 0 to positive infinity, but I don't know if that, right at 0, if that's considered concave up or not. It depends on the textbook, and it depends on your teacher. So this is why you cannot just assume when you get x equals 0 here as a critical value that it is automatically a point of inflection. Here is a classic example where a critical value ends up not being a point of inflection. In our next problem, we are asked to find the points of inflection of this function here. As soon as we see points of inflection, we know we're going to have to take the second derivative because we do not have the graph of the first derivative. We're going to find the critical values of f double prime. We're going to find where f double prime equals 0 and where f double prime is undefined. Okay, first, if f double prime equals 0, the focus is on the numerator. Folks, this expression here is not factorable, so we will have to use the quadratic formula. Now, the first thing I would do here is I would look at the discriminant, because if the discriminant is negative, then there is no real value of x that would make this function equal to 0, this second derivative function equal to 0. So here, if we do the discriminant, it's b squared, which is 4. Let me just write it here. B squared minus 4ac. So it's going to be 4 minus 4 times 1 times 4. And you can see we have 4 minus 16, which is negative, meaning there is no value that will make that second derivative 0. So let's focus here on f double prime being undefined. F double prime will be undefined if the denominator is 0. So x equals negative 2 and x equals positive 4 will both create that scenario. So we need to do a sign analysis on these two critical values. There's negative 2 and there's positive 4. Now folks, in the interest of time, I went ahead and did this ahead of time. And when we do, we find that it is Second derivative would be positive here, meaning the graph would be concave up. It is negative in this location, meaning the graph of f would be concave down. And finally, the graph would be concave up here. That would lead us to believe that -2 and +4 are both points of inflection. But as I mentioned earlier in the video, you have to go back and make sure these points exist on this function. And they don't. Look, this is evident right from the get-go that this graph is going to have vertical asymptotes there. So here is the graph of the function. Here is our vertical asymptote at x equals -2, at x equals +4. This function is bottom heavy, which means it's going to have a horizontal asymptote at y equals 0, and you could see, indeed, it's concave up from -infinity to -2. It's concave down from -2 to +4, concave up from +4 to +infinity. But folks, those are not inflection points. In our next problem, we are given that f equals x to the 2/3 power, and we're asked to find the local extrema. So in this case, we have two options. One, we can do the gold standard, which is we could take the first derivative, set it equal to 0. Sorry, that should be first derivative. First derivative equal to 0 and first derivative equal to undefined. That'll give us our critical values. Then we would do a sign analysis on the critical values, and we would see if the graph changes from increasing to decreasing or from decreasing to increasing, and in those scenarios we would have a local minimum or local maximum depending on which critical point we are talking about. Option 2, folks, is to use the second derivative test. Recall, the second derivative test is a shortcut in some ways, but the second derivative test relies on the critical points from the first derivative. You do not do a sign analysis. You take the second derivative of each critical point. And depending on what you get, if you get a positive value, that means f would be concave up, and that critical point would be a relative minimum. And the opposite happens. If you get a negative value when you do f double prime of the critical point, you would get a concave down portion of f that you're talking about, and that would be a relative maximum. But let's go ahead and use the gold standard here, and let's go ahead and use the first derivative and then do a sign analysis thereof. So here is the first derivative of this function. We're going to set f prime equal to 0 and f prime equal to undefined. Now, f prime equals to 0 does not exist. That numerator would never be 0. However, the graph is undefined at x equals 0. The graph of f prime, I should say. Now we're going to do a sign analysis of f prime here. 0 is our critical point. That 2 is never going to be a negative. That 3 is never going to be a negative. Therefore, we are only doing a sign analysis of the cube root of x. And in essence, we don't even have to put it in a fraction here. We could just be looking at the denominator. Okay, in zone 1, I'm going to use -8 because I'm dealing with the cubed root. I'm going to have something that's cube root friendly, and I'm going to get a negative value here. And in zone 2, where x is greater than 0, I'm going to use +8, and I'm going to get +2 as our answer. So we know, folks, that this graph is decreasing here and it is increasing here, and this will be a local minimum. Now, the importance of this is recognizing that you can't forget to set it to f prime is undefined. If you just relied on this, you would have missed that local extrema. You have to set it to both equal to 0 and equal to undefined. Now, this is what this graph looks like. It looks like this. This is f equals x to the 2/3 power. So you could see it is definitely decreasing from negative infinity to 0, and it's increasing from 0 to positive infinity. And right here, you could see that that is a local minimum, but that is not differentiable. That's one of the examples where the original f function is continuous at x equals 0, but it is not differentiable. You see it also in absolute value functions where there's a point. You will also see it when you have vertical tangents, a graph that does this, say, has a vertical tangent right there. That also would be not differentiable, though continuous at x equals 0.